In this video, I'm going to outline how to do these Kirchhoff questions from the assignment. First, we'll start with question number 2, which is fairly straightforward. Here, in these questions, we don't have junctions. So therefore, we have to use Kirchhoff's second law. In this first question, there is only one loop. So, if we now look at the rule we're applying, which is that the summation of all the voltages equals 0, that is, if I take the EMF and subtract all the PDs from it, I should end up with 0. Now the EMFs, let's have a look at the 3 rules. We need a single loop. Yes, tick. 2, we need the direction of the currents drawn. Also provided. And now we need to consider conventional current. I'm going to start here and I'm going to move with conventional current this way. So let's have a look at the EMFs. There is only one EMF in the entire loop. So therefore that EMF has a value of 6 volts. Let's have a look at the potential differences. Again, using conventional current, we're going to come to the first resistance. What is the potential difference across here? Well, we know that V equals IR. The current is moving in the same direction as we are. It's moving in the conventional current direction. So therefore, IR is positive through this resistor. The value of the voltage would therefore be I times 3. If we go round to this resistor, similarly, the voltage or potential difference across this resistor would be current I times 2, IR. If we express that as an equation, we end up with 6 volts EMF minus the potential difference, I3 plus I2. So 6 equals 5I, and if we do the math, we end up with a current of 1.2 amps. If you haven't been able to follow this, you need to ask for some help. So put your hand up and have a word with me. Question 2 is very similar. It's different in that now there are 2 EMFs. If we consider conventional current, the direction we're moving in, we can see that the 2 batteries are actually working with each other. They're not cancelling, in fact they're adding. So now when we do our summation of EMFs, so we can consider this equation, then the total EMF in the circuit is 6 plus 4. So we've got 10. If now we consider the potential difference, the PD, we need to consider the current, I, times 3. Now the current, I, is moving in the same direction as we are, so it's positive. So our PDs, once again, are 3I plus 2I, which gives us an EMF of 10 and our PD of 5. When we do the math, we end up with 2 amps. Question 3 asks us to start using Kirchhoff's first law. Summation of currents at a junction is equal to 0. You can see that the current is drawn in the picture. So we need to build an equation for this junction. Now the current coming into this junction is I2 and this current here, which is 0.05 amps. So our equation would be I2 plus 0.5 amps would equal the current coming out of the junction, which is 1.26. Once we have it expressed as an equation, we can now rearrange it to find the value of I2, which is 0.76 amps. B isn't really a Kirchhoff's question, it's simply asking you to use V equals IR. What is the potential difference across here? The potential difference would be equal to the current times the resistance. So it would be 0.76 times 66, which gives you 50.16. In the third part, you have to find the potential difference across here. Now you could use normal circuit calculations, but we're going to use Kirchhoff's second law. And the second law is that the sum of the voltages, the total voltage, is equal to 0 in a loop. We need to find a loop. So what we do is we consider only this loop here. Note that there is no EMF in that loop. That still works mathematically. What we need is any loop. So let's have a look here. If we draw that single loop, we're left with our diode, whose potential difference we need to find, a resistor of 48 ohms, and a resistor of 66 ohms. We have a current flowing this way in this section of the circuit equal to 0.76 amps. In this section of the circuit, we've got a current of 0.5 amps. Now this is all information in the question. So let's use this equation. First of all, what are the EMFs? There are no EMFs in this circuit. So because there's no EMF in the circuit, the net PD in this circuit has to equal 0. Okay, so I'm going to try and solve this, and it doesn't really matter which direction I move in. So I'm going to take this way, I'm going to go this way as positive, right? And you can see that what I'm going to find is that this PD plus this PD plus this PD is going to equal to 0. So let's see how that works mathematically. In this direction, this PD is equal to 66 times 0.76. Is it a positive? Yes, because I'm moving in the same direction as the current. Now, we're going to add that to the next PD. Plus 48 times 0.5. But wait. This current is going opposite to the way I'm moving. So actually it's 66 times 0.76 minus 48 times 0.5 minus 0.5 times R. And you can see that here in the equation. So this is a statement that describes the PD in this loop. The next step is to do the maths, and you should end up with a value of R of 52.32. So let's try question number 4. Here we have what looks like quite a complicated circuit. But once again, we're going to try and keep it as simple as possible. Remember, you're just interested in finding loops or junctions. Here we have a really simple loop here with only one resistor in it. If we use this section here from the 9 volts around the outside, then we have another loop with 2 resistors. There's really no need to use this loop around here because that would give us 3 resistors. Now, what are we trying to find? We're trying to find V1 and V2. So we're going to use 2 loops. This loop first and this loop second. If we look at the answers here, you can see how I've used that first loop. If the summation of the EMFs equal the summation of the PDs, or better still, the summation of all the voltages in total have to equal 0. So what I'm doing here is building my equation by first looking at my EMFs. My current directions are arbitrary. I've just drawn them this way to follow conventional current. Conventional current, remember, is the positive charge moving around the circuit. So I'm taking this positive plate and assuming the electron is moving this way. Okay, like this. That's why I've drawn these arrows in. If they're wrong, then my answer will be minus. So I'm not too worried about it. Now I'm going to start here and I'm going to add up my EMFs. 6 plus 9 equals 15. They're working in the same direction, so that we're adding them. Now, what is that equal to? The PDs in the loop. There's only one, which is this one here. Now, this PD has to be equal to 15 in order to balance the EMF. Now I'm going to find V2. If I bring the other circuit, the other loop, I can see that there are two EMFs. And I'm going to follow the conventional direction this way. And what I can see is that I've got an EMF of 9 volts plus 8 volts here, which gives me 17. That is my EMFs. My PDs are 3 volts plus V2. Added together, these two must equal 17. So the answer is, when I do the maths, the unknown V2 equates to 14 volts. And that's question 4. These are our questions for question 5. We have 2 circuits. In the first circuit, we have 2 EMFs and 2 resistors. The currents are labelled, and we need to find the value of the currents in the question. The first thing we need to do is to use the junctions to set up a statement for currents. So I'm going to look at this question first. Using Kirchhoff's first law, I can see that current 1 comes into the junction and then splits into I2 and I3. You can see that here in the original question. I1, which goes all the way around here, I1 equals I2 and I3. So our equation will reflect that. I1 equals I2 plus I3. Now I'm going to look at my first loop. I've chosen a simple loop with only one resistor in it. And that would be the 6 volts and the 3 ohm resistor. The summation of my voltages will equal 0. That means that this EMF will be equal to 3 ohms times the current. I'm moving this way because it's the conventional current, and the current inside my resistor is also in that direction, so it's positive. And I write my statement, I'm left with 6 volts equals 3I, so therefore I1 is equal to 2 amps. I now need to see what's going on in the second resistor, so I've drawn my second loop. In this loop, the currents I3 going through the 2 ohm resistor is also in the conventional current direction. So I'm going to start here and go around, and I find there's only one EMF, and that EMF is equal to 4 volts. My PD, well, there's only one PD, which is 2 ohms times I3. 2 ohms times I3. So therefore, if I rearrange this equation, I3 is equal to 2 amps. I now need to go back to this first equation. I1 equals I2 plus I3. If I rearrange using the two values that I've got, I find that I2 equals 0. So no current goes through that part of the circuit. The current I2 is equal to 0. In the next circuit, we do exactly the same. But the only difference here is that we do find that sometimes the current going through the resistor is in the opposite direction. Have a go and see if you can do it on your own.